Hi, in this lecture, we'll be talking about what is science and what makes science trustworthy. So there's a lot of research looking at how much the general public trusts science. And this data from the United States shows that public trust in science is really high. So the green bars here are Americans' responses to the question, how much do you trust scientists? The light green is a fair amount and the dark green is a great deal. So overall, between 76 and 86% of Americans trust scientists at least a fair amount. And that's about as high as we see for any institution in the US. So that's about how much Americans trust the military. And it's higher than Americans trust business leaders or elected officials or religious leaders. So public trust in science, at least in the US and many other countries, is really quite high. But this is somewhat surprising because the very same survey also asked the respondents to report on whether they believe that scientists are provide fair and accurate information, admit mistakes and take responsibility for them, and are transparent about conflicts of interest, things that you might expect from trustworthy scientists. And the respondents' answers were actually quite negative here. So the green dots here are the proportion of respondents who said that scientists do these things. So the first row is provide fair and accurate information. And the first column is medical scientists. So 32% of respondents said that yes, medical scientists provide fair and accurate information. 24% said nutrition scientists do, and 35% said that environmental scientists do. For the last row, admit and take responsibility for mistakes, you can see that most Americans actually don't think that scientists admit and take responsibility for mistakes. So this is kind of surprising. It seems like a paradox that people trust scientists a lot, but not because they think that scientists are noble and always do the right thing. So this raises the question of what is it that makes science trustworthy if it's not that scientists always admit and take responsibility for their mistakes? This question has been answered by some philosophers of science and sociologists of science who talk about the social process of scientific communities creating a trustworthy body of knowledge. So for example, psychologist Don Campbell talked about how the resulting dependability of scientific reports comes from a social process rather than from dependence upon the honesty and competence of any single experimenter. He said, organized distrust produces trustworthy reports. So it's because scientists agree to have a certain level of distrust of each other and to check each other's work, to ask to see the data, etc., that we can have a system that is trustworthy, even if the individuals in it sometimes are defensive or don't always admit their mistakes. This was echoed in a quote by a historian of science, Naomi Oreskes, who you have a video by her in your assignments this week. And she talked about how we know that science is trustworthy. And she said that we know this the same way we know that other empirical claims are true. We observe, we collect observations and see if the claim is borne out in the evidence. And she said, when we observe scientists, we find that they have developed a variety of practices for vetting knowledge, for identifying problems in their theories and experiments, and attempting to correct them. So again, this idea that we have a system, we have ways to keep each other accountable that creates a trustworthy community and outputs. This is very idealistic. It would be great if this were true, and I think it's an ideal that scientists strive for. But I think it's actually a harder question to answer. Why is science trustworthy? We can appeal to these ideas of organized distrust and verifying and checking each other and correcting them. But it's actually a lot harder to point to those mechanisms. What does it look like when scientists do that? And that's one of the things we're going to talk about this semester. I'm going to now quote from a tweet from James Heathers, who's a very prominent scientist and sometimes critic of bad science. And he said on Twitter, "Science is self-correcting, sure, when we correct it, not because of magical progress." So there's nothing magical about science that makes it inherently self-correcting. We have to actually do the self-correction. So these communities of verifying each other, organized distrust, need to actually take steps to ensure that this happens. These ideals are also echoed in Robert Merton's work. He was a sociologist of science writing in the 1940s. And he talked about 4 norms or values that are shared by scientists. And again, this was kind of looking back, this looks quite idealistic. These are norms that maybe scientists strive for or ideals in science, but not necessarily an accurate depiction of how science always works. Maybe science at its best works this way. So these 4 norms are universalism, which is the idea that we decide whether a scientific claim is valid, not based on who said it, but based on the content of the claim itself and the evidence for it and so on. So the validity of a scientific claim doesn't depend on who's making it. It doesn't matter if you're famous. It doesn't matter if you're at a prestigious university. We're going to evaluate your scientific claim the same way, regardless of who you are. So there shouldn't be hierarchy. Status shouldn't matter in the context of evaluating the validity of a scientific claim. This is really important for self-correction because if we don't have this norm, then the people at the top can make mistakes or make invalid claims and it'll never be corrected. So you can see why universalism is really important for a system that prioritizes self-correction. The second norm is now called communality. It used to be called communism. And this is the idea that the findings of science belong to everyone. They're not private property, so there shouldn't be much secrecy. Open communication should be key. Again, you can see why this is really important for self-correction. We can't find the errors and correct them if people aren't open about what they did. The third norm is disinterestedness, and this is the idea that scientists should be interested in finding the truth and not in their own personal gain or success. And this is a controversial one because it probably doesn't line up with how scientists actually work. We probably have a little bit of motivation for our own gain and a little bit, or maybe a lot of motivation for finding the truth, but it's a mix of things. But the ideal is that we shouldn't factor in self-interest. We should report the truth, whatever we find, even if it makes us look bad, even if we have to take back something we said earlier. So this is important for self-correction because we have to prioritize what's correct over what's best for an individual. And then finally, the last norm is called organized skepticism or organized distrust, as we saw earlier. And this is the idea that we don't just take things at face value. We expect others to want to see our work. We expect to ask to verify each other's claims. And it's not okay for a scientist to just tell another scientist, oh, no, just trust me. I'm not going to show you how I got that result. And this applies to everything in science. Every scientific claim should be open to skepticism, distrust, scrutiny. It doesn't matter how much we wish the claim were true, if it lines up with our moral values, our religious values, our political values. It's okay to question a scientific claim regardless of its implications. So there was a survey done a few years back asking scientists what they think about these norms. So these norms were presented in plain language to a group of scientists, and the scientists were asked, do you agree with these norms or do you agree with the counter norms, the opposite? Do you behave according to these norms? And do you think other scientists behave according to these norms? So I'm going to show you those results. The gray bars, the majority of people in the top two bars, are people who agree with the norms, who say, yes, in principle, I agree with these norms. The black part of the bar are people who agree with the counter norms, secrecy, hierarchy, etc. So almost no scientists prefer the counter norms, and almost all scientists say they agree with Merton's norms. When asked about their own behavior, here we see a little bit more of a mix. There are fewer scientists who say, yes, my behavior is in line with these norms, but there's still relatively few scientists that say, no, my behavior is in line with the counter norms. And then the third set of bars is the result when they ask the scientists, how do you think other scientists behave? And here we see that actually most scientists are quite cynical and think that other scientists behave in accordance with the counter norms, are secretive, hierarchical, self-interested, etc. So this raises a lot of questions about which is more accurate, how scientists see themselves or how they see others, and how good of a job do we actually do at living up to these ideals that promote self-correction and organized distrust among the community. So what I'm going to talk about for the next few minutes is the systems we would need to maintain for science to really rise to this ideal of prioritizing self-correction. So what do the self-correcting mechanisms of science look like? So one important one is transparency. So transparency is fundamental to self-correction. It's in line with the communalism norm that we just talked about from Merton. It's the idea that things should be open. So I should share the data, for example, behind my claims. I should share the details of how I obtained my data, the procedures, and so on. And this idea seems pretty intuitive, and hopefully it's intuitive to you that scientists should share their work. But there's also another reason why it's really important for scientists to be open and transparent. And this is linked to an economic paper that talked about what happens in economic markets, and we'll get back to science in a minute, but in economic markets when there isn't transparency. So when someone who's selling something, say a car, can hide the details of what state that car is in, for example. So this happens, for example, in the used car market. So people don't always disclose everything about like what accidents the car has been in or what kind of shape it's in. And when that's the case, there's an information asymmetry between the buyer and the seller. So the buyer knows less about the car than the seller. They know that there are things that the seller knows that they're not disclosing. And this information asymmetry leads to what Akerlof, the author of this paper, called quality uncertainty on the part of the buyer. So the buyer knows that there's information they don't have. They know about this information asymmetry, and therefore they become uncertain about the quality of the car. They know that they can't tell a high quality car apart from a low quality car. And when that happens, when they know that they can't tell the difference, and there's an incentive for the seller to only sell low quality cars because those are cheaper to get, and they can pass them off the same way they could pass off a high quality car, then the buyer loses trust in the market. So he showed mathematically that this information asymmetry leads the buyer to have quality uncertainty, which leads to not being willing to trust the market, not being willing to invest in the market. And these same principles apply to science. So a scientist who made a new discovery is basically like a seller trying to convince other people that their finding is credible and trustworthy. And if they withhold information, if they say, I'm not going to show you how I got my finding, I'm not going to let you reanalyze the data, it's like a seller of a car saying, I'm not going to let you look under the hood. And it creates an information asymmetry where readers or other people considering whether or not to believe this claim, they know that there's information they're missing. They know about this information asymmetry, and they now find themselves in this state of quality uncertainty. They can't tell the high quality scientific claims apart from the low quality scientific claims because they're lacking the information to do so. So that quality uncertainty leads to this vicious cycle where the sellers, in this case the scientists producing the new work, have very little incentive to produce high quality work. If they don't have to disclose all the information, if they don't have to be transparent, then they could do low quality work and it won't look very different from high quality work. Other people won't be able to tell the difference. So then that quality uncertainty on the part of everyone else reading the claims, they think, oh, well, I can't tell the difference between high and low quality work. There's no incentive for the researcher to do high quality work when they can get away with low quality work. So therefore I start losing trust in the whole enterprise and not being willing to invest in that whole enterprise. So I argued in a paper that we actually need transparency, not only because it's the right thing to do, but also because if we don't engage in transparent research, then other people are going to be less and less willing to trust us, and it'll lead to this vicious cycle of quality uncertainty and then lack of trust in the system. So one of the really important necessary components of self-correction in science is transparency. So we need it to be able to detect errors. We need it to be trustworthy, otherwise people will lose trust in us. But transparency is just one component, and it's not enough. So this was articulated really well in a paper by Andrew Gelman called Honesty and Transparency Are Not Enough. And he said, consider the practical consequences for a researcher who eagerly accepts the message of ethical and practical values of sharing and openness. So a researcher who agrees that transparency is important, but does not learn about the importance of data quality. So they're transparent, but they're not as concerned with quality. Gelman said, this person could then just be driving very carefully and very efficiently into a brick wall, conducting transparent experiment after transparent experiment, and continuing to produce and publish noise. So basically they could be doing very shoddy research very transparently. So the transparency is not enough, right? Transparency is necessary for identifying errors, but it doesn't mean you're doing good work. So it's a first step, and it's a necessary step, because only with transparency can we find the errors, correct them, and then improve our work and earn more credibility. But that's not necessarily how it'll go if we're more transparent. So another possibility is that we become more transparent with our research, but it turns out that research is really shoddy, has lots of flaws. We get persistent, devastating criticism. We don't learn from it. We don't improve. We keep doing shoddy work, and then we lose credibility. So transparency is necessary for credibility, but it's not sufficient for credibility. It doesn't guarantee credibility. Transparency only guarantees that you'll get the credibility you deserve. And what makes the difference between getting more or less credibility is the quality of your methods. So everything we're going to learn this semester is vital for making sure that we're doing science in a way that's trustworthy, that's credible, and that's self-correcting. So there are two parts to this. The first is transparency, which we won't talk about much. What we'll spend a lot of time on this semester is quality, what it means to do high quality research. That's obviously really important in and of itself, that we want to be doing high quality research, but it's also important because if we honor the values and goals and ideals of transparency, we're going to be held accountable. We're not going to be able to hide shoddy research behind the wall of secrecy. So we should be transparent, but that means it becomes even more important that our research is really high quality, that we make as few mistakes as possible, that we learn from our mistakes and improve our methods all the time. So hopefully everything we learn in this course will help with that quality aspect of research methods. All right, let's move on to some research methods.